Space agencies are racing to stop a silent threat that takes the vision of 70% of long-term astronauts. For decades, space agencies focused on keeping astronauts alive. Now they are focused on keeping them seeing. The European Space Agency and NASA are tackling a condition known as spaceflight-associated neuroocular syndrome, or SANS. This is not a temporary blur. It is a collection of structural changes to the eye and brain caused by prolonged exposure to low gravity. The data shows that around 70% of astronauts on the International Space Station develop these changes. The root cause is simple physics. Without gravity to pull fluids down, bodily fluids shift into the head. This buildup increases pressure behind the eyeballs. The pressure squashes the eyeballs, swells the optic nerve, and pushes the retina forward. Over time, this can lead to permanent vision damage that does not fully reverse when the astronaut returns to Earth. To understand the stakes, look at the case of NASA astronaut John Phillips. He launched to the International Space Station in 2005 with perfect 20/20 vision. After spending 6 months in orbit, he splashed down with vision that had degraded to 20/100. This is classified as a moderate visual impairment. His eyes changed shape under the pressure of fluid buildup. While his vision improved after returning to Earth, the incident highlighted a terrifying reality. As we send astronauts on longer missions to the Moon and Mars, we cannot assume their eyes will heal themselves in time. The margin for error is vanishing. The solution requires monitoring, but standard eye exams are bulky. The European Space Agency has commissioned a British startup called Siloton to build a new kind of scanner. They are taking quantum technology and shrinking it down. The core components usually found in optometrist offices are being fit onto a photonic chip smaller than a coin. This device can monitor ocular health in the tight quarters of a spacecraft. The technology works by using quantum sensors to detect tiny changes in eye structure that standard cameras miss. It turns a complex medical diagnosis into a routine checkup that any astronaut can perform. Before this tech reaches the stars, it must prove itself on Earth. Siloton is currently working with the United Kingdom's National Health Service. They are enabling patients with retinal conditions to self-scan at home using this same technology. It sounds like a simple home health tool, but the requirements are identical to spaceflight. The device must be robust, precise, and easy to use for non-experts. Ewan Allen, the co-founder and chief technology officer, noted that the space requirements are exactly the same as the NHS requirements. The only difference is the environment. The hardware must survive the vibration of launch and the isolation of deep space. Some commenters on the original discussion pointed out that the root cause is gravity itself. If we could create artificial gravity, we might solve the fluid shift entirely. The debate centers on rotating the spacecraft to generate G-forces. The physics is sound, but the engineering is brutal. One commenter noted that a vessel large enough to provide comfortable rotation is borderline not doable at the moment. The size of the rotating part would need to be huge, or the gravity at your feet would feel different from your head. Another commenter pointed out that building giant spinny rings in space requires mining asteroids. While possible, the cost of 30 or more launches to build it rivals the cost of the mission itself. The community also discussed the tether capsule design as a cheaper alternative to full rings. You could launch sections and build them at a Lagrange point. But as one commenter observed, the amount of G-force depends on how far you are from the axis. If the ship is too small, the rotation makes you dizzy. The consensus is that we are not yet at a point where artificial gravity is economically viable. We are building the cheapest possible version of the ship and staffing it with astronauts who romanticize the hardship. The problem solves itself by endurance for now. The Artemis flights to the Moon are the next test. These missions will last longer than any in history. The Siloton scanner must be flight-ready. If the quantum eye scanner works, it gives us a new tool to track SANS in real time. We can detect the swelling before it becomes permanent damage. It is a small chip, but it might be the difference between an astronaut returning home with a headache or with a lifetime of blindness. The race is no longer just about landing. It is about seeing what is there when you get there. The future of human spaceflight isn't just about surviving the journey. It is about preserving the ability to see the destination. Thanks for watching Orbit Reports. Subscribe for more precise science briefings.